At its heart, Bayesian analysis is really about something we all do. Every single day, we start with a belief, we see some new evidence, and then we update that belief. So the big question is, can we do that with some real mathematical rigor? Well, it turns out we can. And that simple idea, it's changing everything from science to AI. Okay, let's dive in. Here's our game plan for today. We're going to start with the big picture, the core concept of Bayesian thinking. Then, we'll roll up our sleeves and get into the theorem itself. After that, we'll see how it stacks up against the other big school of statistics, explore why this 250-year-old idea is suddenly everywhere, and then wrap things up with a look at its huge impact on the real world. All right, first up, a framework for belief. You can think of this as the philosophy behind the formula, basically a formal system for how to change your mind. Let's really think about this for a second. Imagine you've got a hunch that a new marketing campaign is working. Then you see the first week's sales data. Suddenly, that hunch gets stronger, right? Well, Bayesian inference is the engine that actually quantifies that feeling. It gives us a logical way to reason and learn, especially when we don't have all the facts. And the idea is named after this guy, Thomas Bayes. He was an English minister and mathematician, and his most important work was actually published after he died. But the story doesn't stop there. The French mathematician Pierre-Simon Laplace was a huge player. He came up with the same ideas on his own and really ran with them, applying them to massive problems, like calculating the mass of Saturn. He's the one who really turned the theorem into the powerhouse tool we know today. Okay, let's build on that and get into the mechanics. Time for section 2, deconstructing Bayes' theorem, the engine of inference. And here it is, the big one. Now, I know formulas can look a little intimidating, but trust me, we're going to break down every single piece. Because what's so cool about this, what you're looking at right here, is the official recipe for blending what you used to believe with what you're seeing right now to create a brand new, smarter belief. So it all starts with the prior. This is your starting point, your belief before you see any new evidence. It's just a formal way of stating your assumptions. So, for example, before you flip a coin, your prior belief is probably that it's a 50-50 shot for heads. That's it. It's the starting line for our entire analysis. Next up is the likelihood. Now, this is the crucial bridge that connects your belief to the actual data. It answers a really specific question. If my initial belief was true, how likely is it that I would see this exact evidence? So if you believe the coin is fair, the likelihood of seeing 3 heads in a row is, well, it's pretty low. This is how the data gets its voice. And all that work leads to this, the grand finale, the posterior. This is what it's all about. It's your updated belief after you factored in the new evidence. You take your prior, you mix it with the likelihood from the data, and boom, you get a new, more informed state of knowledge. This is the goal. To put it all together in a much simpler way, just think of it like this. Your new belief, the posterior, is just your old belief, the prior, multiplied by how well that old belief explains the new data, the likelihood. And what's really cool is that it's a continuous loop. Today's posterior just becomes tomorrow's prior. It's like a mathematical learning machine. Now, to really get why the Bayesian way of thinking is such a big deal, it helps to understand what it's not. And that brings us to the great statistical divide, 2 very different views of probability. Okay, this slide gets right to the heart of a debate that's been raging in statistics for a century. For a frequentist, probability is all about the long run. If you flip a coin 1,000,000 times, the probability of heads is just the percentage of times it landed heads. That's it. The coin's true fairness is some fixed number we're trying to figure out. But for a Bayesian, probability is a degree of belief. It's about our uncertainty. The coin's fairness isn't a fixed number. It's something we have a belief about, and we can describe that belief with a distribution. And this quote just nails the philosophical clash. See, Bayesians argue that by forcing you to state your prior belief up front, the whole process is way more transparent. All your assumptions are right there on the table for everyone to see, to debate, and even to change. The thinking is, hey, it's better to be honest about your starting point than to pretend you don't have one. Of course, frequentists, whose methods were championed by giants like Ronald Fisher, have a comeback. They argue that choosing a prior is just too subjective. But then Bayesians fire back and say, well, what about choosing a p-value of 0.05? Isn't that just as arbitrary? The whole debate really comes down to where you want to make your assumptions, at the beginning or somewhere else in the process. So that leads to a pretty obvious question, right? If this theorem is over 250 years old, why does it feel like it's exploding in popularity right now? That takes us to our next section, from theory to practice, the Bayesian revival. This timeline really tells the story. For a very, very long time, Bayesian methods were mostly just a cool idea sitting on a shelf. Frequentist statistics completely dominated the 20th century, mainly because the math was just easier to do, especially in a world without powerful computers. It's kind of wild that the term Bayesian wasn't even really coined until the 1950s. So what was the magic spark? What finally changed? In a nutshell, computers. Raw computational horsepower. The math behind most real-world Bayesian problems is just mind-bogglingly complex. Often, it's impossible to solve perfectly. But with the rise of super-fast computers and the invention of these incredibly clever new algorithms, we could suddenly get really, really good approximations. Technology finally caught up with the theory. And that brings us right up to the present day with our final section, the Bayesian revolution today, where we get to see this stuff at work in the real world. I mean, just look at this list. This is where it gets really exciting. This framework has gone from an abstract idea to an absolutely essential tool. It's being used to design smarter, faster clinical trials for new drugs, to help us understand the uncertainty in our machine learning models, and to make better decisions in fields as different as sports analytics and aerospace engineering. It's everywhere. So if you walk away with just one thing today, please let it be this. Bayesian analysis is so much more than a formula. It's a complete, logical, and powerful framework for thinking about uncertainty. It's a system for taking what we already know and rigorously combining it with new data to learn more about the world. Which leaves us with one last big thought to chew on. We now have the tools to apply this incredible system of reasoning to almost any problem we can think of. So as we get better and better at this, how is it going to change the future of science, of business, and of discovery itself?